Hey, everybody. This week, so instead of having myself and Ben, your usual hosts, I'm here with a special guest, Professor Stuart Russell of Berkeley, who's written a really fascinating book about AI and the future of AI. And we're going to talk about it. Professor Russell, thank you for joining me.
It's a pleasure.
You are listening to Linear Digressions. So, Professor Russell, I know your name might be familiar to a lot of folks who are listening to this podcast, but for those who don't know your work as much, or they maybe recognize the name but aren't quite sure how to place it, do you mind giving a brief introduction?
Sure. I've been at Berkeley longer than I care to remember, about 34 years. And I've been doing AI actually since I was in high school. I wrote a chess program back around 1975 in high school. I've been doing AI a long time. You might know my name if you've taken an AI course. You probably used a book by Russell and Norvig. So Peter Norvig and I wrote that starting in 1992. We just sent the fourth edition off to the printer last week.
Congratulations.
So my research has covered pretty much every area of artificial intelligence: reasoning, learning, problem solving, game playing, planning, robotics, language, vision. These days, I'm concerned about the following simple question, which we had actually in the first edition of the textbook. What if we succeed?
There's a new book that you have out now, Human Compatible: Artificial Intelligence and the Problem of Control. As you mentioned, it sounds like this is something you've at least been aware of for a long time. I wanted to ask what motivated you to write this book now?
So the book sort of has two parts. One is the part that says, okay, this is how we currently think of AI, and this is why it's extremely wrong. If we pursue the current standard model of AI, as AI systems get better and better, we face the prospect of losing control over them and losing control to machines altogether. The second part of the book says, okay, here's how to fix it. Here's a way of doing AI on a completely different kind of general theoretical foundation and conceptual framework. And in this new framework, it seems that at least that failure mode of losing control to machines seems to go away. So why I wrote now is because sometime around 2013, 2014, I figured out what the second half of the book should be, namely, here's a way of dealing with the problem. I didn't just want to write a book saying, okay, we're all doomed.
Right.
Already, and Alan Turing actually in 1951 said, we're all doomed. So that wouldn't be a new point.
So without asking you to cannibalize your book sales too much here, in a snapshot, what is the fundamental way that we've gotten it wrong for a long time, and where is the ray of hope that you found in that second half of the book?
So the standard model of AI involves building machinery that optimizes a fixed known objective. So if you've read the first few chapters of the book, the textbook, we talk about, for example, problem-solving systems that find a sequence of actions that's guaranteed to achieve a goal with minimum cost. So there you have to specify the goal, you have to specify the cost function. In Markov decision processes, you have to specify the reward function. In machine learning algorithms, you have to specify the loss function. In control theory, you have to specify a cost function. So in fact, it's not just AI, it's a good fraction of 20th century technology is based on this model. And the model is wrong because we do not know how to specify objectives correctly, particularly when you have systems that start to operate in the real world. It's easy on the chessboard to say, okay, you're supposed to win the game. But in the real world, you might say, okay, I'd like you to restore carbon dioxide levels to pre-industrial concentrations so that we can get the climate back in balance. That sounds great. What a wonderful objective.
Yeah, what could go wrong?
What could possibly go wrong? Well, you'd get rid of all the people because they're the ones who are producing the carbon dioxide. And then you might say, okay, well, let's not do that. Let's restore carbon dioxide and not kill anybody. And then, of course, the system has a very subtle and complex social media campaign that convinces everyone to have fewer and fewer children until there are no people left, and then carbon dioxide is restored. And that's much easier than trying to do all the politics of convincing people to stop consuming and producing and all that kind of stuff. So actually, we've known this for a long time, right? We have the story of King Midas. He gave his objective specification, everything he touches has to turn to gold. And of course, it was the wrong objective. And he died because his food and his drink and his family turned to gold. And the genie, you get the 3 wishes. Your third wish is always, please undo the first 2 wishes because I messed everything up. Right, so we know this, and yet we persist with a model where the more effective, the better the AI, the worse the outcome is going to be for human beings. And if that isn't a bad engineering model, I don't know what is, right? So I think we should abandon that way of doing things. In brief, the solution is to say that the machine's objective is still to satisfy human preferences about the future, but the machine knows that it doesn't know what those preferences are. So it's explicitly uncertain. And just to give you a simple analogy, when you go to a restaurant, the restaurant doesn't know what you want to eat. They know that they don't know what you want to eat, and so they ask you, what would you like to eat? Mm-hmm. Or they give you a menu of choices. And if you pick something off the menu, that isn't their life's objective at all costs to give you that thing. If they're out of that item, they're not going to, traipse all over the city trying to find more of it. They'll say, well, sorry, sir, we're out of the duck tonight. Or, the chicken's not so great, but maybe I could recommend the pork medallions instead, or whatever it might be. So this is perfectly normal and understandable to human beings, that we don't know what other humans want, and we ask them, or they tell us, and we have an interactive process. And we can do the same thing with machines. The machine knows that it doesn't know what humans want, but it has to somehow act in a way that is beneficial to us. So it's naturally motivated. So if it's trying to solve that problem, the solution to that problem is to do things like ask questions, ask permission before you kill everyone to restore carbon dioxide levels. You ask, I understand about the carbon dioxide. Is it okay if I kill everyone? And then you could say, no, that's not what we had in mind.
I prefer that you're not, right? Yeah.
So that's the basic goal, and we can formulate this mathematically. If you're interested, it's a problem in game theory, and the solutions to those games have the property that the better the AI, the better the outcome for human beings.
And so as a person who has a strong technical background here, as well as, reading the book, it's clear that you're also thinking about, the social implications, the philosophical implications, there's economics entering the picture in the form of game theory, putting all of that together, how optimistic are you that let's start with the technical level, that this is something that is computationally tractable. It's something that it's realistic to think that we could implement. Does it feel like a solution sort of from those angles as well?
Great questions. So I think part of what we have to do, besides convincing everyone that they're wrong, or they've been misled. Let me put it that way, and partly by me, because the AI textbook editions 1, 2, and 3, espouse the standard model of AI. Mm-hmm. We have to convince people that this new approach is a better one, and I think it is. Even in the short term, this is not just about losing control and existential risk. This is about how do you design a good personal assistant or a good domestic robot. You don't want the domestic robot cooking the cat for dinner because it doesn't understand the sentimental value of the cat. It should at least ask permission before doing it. So the problem of solving these games, actually, we've been gradually reducing the complexity of that. The game has certain characteristics that make it quite a bit easier than a general game of partial information. So we've reduced it down to no more complex than a certain restricted class of partially observable MDPs or POMDPs. And those are still, in general, those are piece-based compute, but we think that probably it's less complex than that. And we're able to now solve, decent-sized instances of these games and exhibit these kinds of behaviors. So, surprisingly, it's not just what is the machine's solution to the game. It's also, well, how does the human behave, since they're part of this game as well? And they do things like show the robot what not to do, right? Which, of course, you would never do. I mean, the human by themselves wouldn't be doing that, right? So the robot, seeing the human showing the robot what not to do, has to understand that the human isn't showing him what to do, he's showing him what not to do. And since they both solve this game, then they both understand the sort of code of communicating information. So the defining characteristic of this approach to AI is that at runtime, information flows from the human to the machine about what human preferences are. And you can set up all kinds of different protocols for what that information flow looks like. It could be in the form of demonstrations. It could be in the form of just requests. I'd like a cup of coffee, right? Well, that's not a straightforward goal. We don't want that coffee to become the robot's life mission at all costs, including murdering everyone at Starbucks so that you can get to the front of the line, right? It's a communication of preference information, and what it means, that's part of the solution of the game.
So one thing I found myself wondering about when I think of, what are some of the stereotypical uses of what people call AI right now is, I think of my Netflix queue, my Facebook feed, all the pop-up ads that I get. And I'm picking these on purpose as examples of AI that on the one hand has been kind of finely tuned to, I don't know, hit our dopamine receptors in such a way that we're always like, yeah, give me more of that. But we all also kind of have these conversations where we back up a step and say like, oh no, that's not good. So when it comes to something like the AI understanding what my preferences are, like, do you think that there's some subtleties in how we would have to think about those kinds of problems where like we kind of are, let's say in some cases, giving it clues about our preferences that are not actually telling it something that's truly what we prefer, let's say?
Yeah, I think social media is a very interesting example. So it's one case where, at least according to most commentators, AI is already destroying the world. And it's doing so because you've released learning algorithms that have a fixed objective, typically maximizing click-through or engagement or some metric that's closely related to income for the platform. And the algorithms optimize that objective, and they don't care what they do to you. You are just a stream of clicks. And in fact, it's not just that they learn to satisfy your interests. They actually modify your interests because that's what reinforcement learning algorithms do. They change the state of the world to get more reward. And you're the state of the world, so they change you to get more reward. They're like drug dealers who keep upping the dose to get you more and more addicted so that you have to keep spending money. And it just so happens that what they're driving you towards is being predictable. They don't particularly want you to be a neo-fascist or a violence addict or a porn addict. They just want you to be predictable so that whenever they send you something, you click on it. But it turns out that the way to make you that person is to drive you to one extreme or another of whatever spectrum you're on. So what's going wrong there actually is several things, I think. One is that The opportunity for providing negative feedback to the system is very limited. So you can fail to click on something, but that's, that could just be because you're having a cup of tea, or because it could be that you find it utterly repulsive that it sent you that thing. And you don't, in most cases, you don't get the opportunity to say that. So you get this one-sided feedback. But also what the algorithm is doing is actually violating one of the tenets, which is that the algorithm is supposed to be satisfying human preferences, not modifying them. And so modifying human preferences is a sort of a failure mode that is already familiar in science fiction, and it's very familiar to any politician. You satisfy people's preferences by modifying them to be easier to satisfy.
Gotcha.
And that's something we absolutely need to avoid, whatever kind of AI system we build.
Gotcha. There's another aspect of your book that I think you've mentioned a little bit, but I wanted to take the chance to ask you about. There's a whole chapter, I think it's entitled "The Not So Great AI Debate," about how you've sort of mentioned it parenthetically, the premise that this is a real threat and that it's something we need to have a serious conversation about now is not universally treated with a whole lot of respect in AI circles. There are lots of people who are very smart and distinguished people who say, for various reasons, that they think the risk is overblown. I'm curious, from your perspective, what is it about this field, do you think, that prompts very smart, thoughtful, insightful people to disagree so much about something as foundational as, is this an existential risk or not?
I think you would see the same reaction in almost any field to someone saying, okay, the work that you're doing, if taken to its logical conclusion, could present an existential risk to the human race. Interestingly, there have been a couple of occasions in the history of physics when the same issue was raised. And actually, I think the physicists responded better. So one was in 1945, when they were very close to developing and testing the first nuclear weapon. And some physicists said it's possible that the nuclear explosion would actually ignite the entire atmosphere. It would create a nuclear chain reaction among the nitrogen atoms in the atmosphere. And so Edward Teller and another researcher whose name I forget actually did the calculations, and they said, we're pretty sure we have a factor of 2 safety margin on this one. So go ahead. And it turned out that, actually, no, they didn't say that. They said, with the size of device that we're testing, it's a factor of 2. But they actually agreed with the objection. I think they said, if you made a sphere of enriched uranium 192 meters in diameter, that would be sufficient to ignite the atmosphere. You might wonder, okay, well, what if they made a little mistake?
Yeah.
Someone else should check the work. And then another one was where, when they were talking about switching on the Large Hadron Collider.
Yes, I remember this. This was when I was in graduate school.
Yeah. Production of strangelets and that kind of chain reaction. So for that case, I don't know enough about the physics to say whether that even made sense. And I think some people thought it didn't make sense, but I believe that they actually took it seriously and produced an argument as to why this actually wouldn't happen. But when you look at the arguments in AI, why do we not need to worry? They clearly don't make sense, right? So well-known AI professor says, well, electronic calculators are superhuman at arithmetic and they haven't taken over the world. Therefore, there's nothing to worry about, right? I mean, a 4-year-old could see through that argument. And in the book, I actually list, half a dozen other ones. And since you're a physicist, there was an objection saying, well, if a black hole was to sort of randomly materialize in near Earth orbit, that would be an existential risk, but we don't spend a lot of time worrying about that. So why should we worry about super intelligent AI?
Yeah.
And the response is, well, if the entire physics community was trying to make a black hole materialize,
that's true. We were not trying to do that. Yeah.
Wouldn't you ask them if that was a good idea? Why are you doing that? And what happens if you succeed, right? And that's all I'm asking. What happens if you succeed? So some AI researchers respond by saying, "Oh, actually, we're never going to succeed."
Well, that's not satisfying in a different way, I suppose.
Right. We're all trying, but we're never going to succeed. And I think the analogy I use is like a bus driver who's driving off the cliff, with the whole human race as passengers, and he says, "I'm driving off the cliff as fast as I can, but don't worry, we're going to run out of gas before we get there." Right? It does not very reassuring.
Yeah, indeed. So I wanted to then hear how is this argument being received? As I'm sure you've been giving talks and writing papers and thinking about this for some time. The book came out late last year, if I'm not mistaken, so had a little bit of time to make the rounds. Perhaps, what from the layperson that you talk to the people who are in pretty rarefied leadership circles to the AI research community. I'm really curious how these arguments are being received.
So far, pretty well. I mean, I don't think I've seen any review that had an argument in opposition to the main points of the book. We have, if you want to sort of look at people with distinguished records, Yuda Pearl, who won the Turing Award in 2011, says that he's a convert. Yoshio Bengio, who just won the Turing Award this year, wrote a very nice set of comments about the book. Danny Kahneman, who's probably the leading psychologist in the world, according to some metrics, and Nobel Prize winner economics, says it's the most important book he's read in quite some time. James Manyika, who runs the McKinsey Global Institute and also is an AI researcher, says it's the most important AI book so far.
Do you think for the folks who are
yet to see sort of much pushback, and they keep inviting me to give talks at all the main conferences, so I guess they like it.
Yeah, that's a good sign. I think my question is also for folks who are listening to this and maybe practicing in this field and who are like, interesting arguments. Maybe they'll pick up the book or give it a little more thought than they gave it yesterday. If there are any other barriers, like what are I'm sure there are barriers. Maybe I'll phrase it this way. What are some of the biggest barriers that you think are still kind of systematically baked into the field of AI that are incentivizing people to keep driving the bus as fast as they can towards the cliff? And that, if we start to have some momentum around the idea that we should change the way we think about this, change the way that we formulate these research objectives, what do you think it will take to implement it from that perspective?
So I think, first of all, the bus driver has to see that there is a cliff ahead. So that's the first step. And then the second step is you have to provide another road, a turnoff. This is what we're hard at work on now, is essentially rebuilding all the technology of AI on this new foundation. Because if you just say to everyone, stop what you're doing, but you don't give them another road to follow. Right?
Yeah, that's tough.
That's difficult to do. And for example, if you're doing supervised learning, which is what a lot of people are doing out there, they would, such a person would ask, well, what else am I supposed to do? I've got data. I'm supposed to train this network. I want to make predictions. But you should ask, what is the loss function that you're using? Mm-hmm. So you don't even have to immediately buy into a whole new theoretical framework with game theory and all that stuff. Just ask yourself, what is the objective that I'm actually optimizing? And is it the right one? And are there externalities that I'm not considering in the effects, think of them as side effects of deploying the system that I'm building. So when you take supervised learning, right, you might say, oh, well, of course, I want to have the highest accuracy that I can. And that's typically what people do, and that's what all the competitions do. And so effectively, they're implementing a loss function, which is what we call the uniform loss matrix, which assumes that all errors are equally costly in the real world.
Yeah.
Right? That assumes that misclassifying, a lime as a lemon is just as bad as misclassifying a person as a gorilla.
Right.
Now, we know from Google Photo that the second kind of error is extremely expensive from Google's public relations point of view. And it was sort of a catastrophe for them. So you should not be using a uniform loss function unless you're pretty sure that's in fact the right loss function. And if you said, well, what should the loss matrix be for classifying images? Well, there's 20,000 categories in ImageNet, so that means a 400 million entry loss matrix. We haven't figured out what numbers go in that matrix, right? We mostly don't know what is the cost of misclassifying an A as a B for every possible A and every possible B. So that means you should be operating an algorithm that has uncertainty about the loss matrix. And once you have uncertainty about the loss matrix, then the algorithm should be sometimes refusing to classify things, sometimes coming back to the user or the designer saying, can you give me more guidance? Is it really bad if I misclassify a lemon as a lime, or a bus as a dog, or cat as an elephant? And gradually you could build up knowledge. But interestingly, there's almost no research on that question. Right? We don't even know how to specify probability distributions over loss matrices.
Yeah.
Especially enormous ones.
Yeah.
So there's a lot of PhD thesis topics. I mean, there are literally hundreds of PhD thesis topics just waiting to be done. And the sooner we do those, the sooner we can provide people with alternative technology. You might call it. So it's sort of like the problem that people face in sustainability. The car manufacturers have been saying for decades, well, yes, of course, you're right, but there's no other kind of car, so we're going to keep making the kind of car that we have. And they're sort of putting the onus on someone else to come up with a sustainable car. And maybe Tesla did that for them.
Well, I think that's as good a call to action as I've ever seen. So with that, I'd like to thank you again for taking the time to come on. Again, the title of the book is Human Compatible Artificial Intelligence and the Problem of Control. Professor Stuart Russell, thank you again so much for joining us.
It's been a pleasure talking to you.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.